Calculus BC, we're in a brand new chapter and a very big jump here in our course. We're moving away from differential calculus, and chapter 5 is going to begin really an introduction to something that we call integral calculus. We're going to work with integrals. We'll define those later, but for right now, what we're really going to focus in on is approximating area underneath a curve with three distinct methods. You can see our learning target up here: LRAM, RRAM, and also MRAM. And those are your three basic methods to do approximations. The L, R, and M will stand for left, right, and midpoint. And RAM stands for really rectangle approximation method. So let's just read up here. For a regular partition of an interval notation, like if you see closed brackets A to B, what that's really saying is your x values are strictly between A and B. X is greater than or equal to A, but at the same time less than or equal to B. We're going to have n sub-intervals. These sub-intervals are always going to lead to rectangles. We're going to have n rectangles. And please look at this right here that I've highlighted in yellow. This is going to be the base of your rectangle every single time. The base of the rectangle will be delta x. And delta x, if you think about it, if we were to go b minus a, that would be the length of your interval, divided equally amongst n rectangle bases, and you would have really the base of each rectangle. So it's just b minus a, the length of your interval, divide by the number of rectangles that you have, and that guarantees that you can find the width that you would have for each and every base. The width would be the same for each and every base here, for each rectangle. So each rectangle has the same base. The LRAM, the left rectangle rule, what you're going to see is this sigma right here means sum. Do some adding up. And F, which would be a y value, is always going to be the height of your rectangle. We just said that delta x is the base of your rectangle. We know that base times height is always going to lead to the area of a rectangle. Let's take a look at LRAM, the left rectangle approximation method. Let's just say you have a curve here. And you can see that you would have n rectangles. You could see, here's rectangle 1, rectangle 2, rectangle 3. Here, rectangle 4, I've even highlighted in blue. What you're going to see is that every base down here is going to be the same. That's your delta x. That's how much x is changing. But look at the height of each rectangle. The height is determined by the left endpoint. The left endpoint right here, you'll say the height on the curve, if you were to just look at this base down below, and I'm highlighting that in black. If you were to just look, and I'm going to change the color right in here just to really make it pop out, make this in green. Look at that base down there. It's that left endpoint that's going to determine how tall your rectangle is. So that's how your y value would be determined. By way of comparison, look at an RRAM. Look, you'd have the same base, but this time, how tall does your rectangle go? Well, not by the left endpoint, but by the right endpoint. The right endpoint, if you were to say, find the point on the curve right here, that's going to determine how tall your rectangle will be, what the height is. So you can see that we'd get some very different looking approximations. In this first picture, the left rectangle approximation, my rectangles are circumscribing. They're going over that curve. We're getting too much area. You can see in yellow, I'm showing that we're actually winding up with too much area. It would be an overestimate if I were to approximate the area underneath the curve. Look at this RRAM though. Your right endpoints, your rectangles don't go all the way to the top. There's a lot of empty space that you're not, dealing with, that you're not approximating. This would be an underestimate. And then we can say, well, what if we had the same base of a rectangle, but what if instead of a right endpoint or a left endpoint, what if we took the midpoint? What if we said, here's your interval, here's your base, and we found the midpoint? What if that would determine how tall your rectangle would be? Well, if that were the case, you can see that kind of looks like it's a little bit better of an approximation. There's a little portion where your area would go over your curve, and then, of course, there's some where you'd be under. But it's kind of looking like maybe they're canceling each other out a little bit. So you might guess that in such a situation here, an MRAM certainly looks like it's a better estimate for finding the area underneath the curve. Well, that seems to definitely be the case here, but the truth is LRAM, RRAM, and MRAM are three very famous methods to approximate area underneath a curve. So we're going to have to know all three of them. And we're going to use all three of them extensively. We're going to use them a lot. So tell you what, we're going to go to our first example, and you can see I've left this up here, a sum sequence. We're going to talk about that in just a moment. It says approximate the area under a curve y equals x squared. And we're going to go from x equals 1 to x equals 5. And we're going to have 8 rectangles. And, depending on the number of rectangles that you have, this could get to be really tedious calculations. That's why up above with that sum sequence, we're going to talk about a nice way how the calculator can actually come to our rescue and help us out. But first, a visual. And I think this visual can be super, super helpful. So we've got this parabola. And let's just say that we're going from, 1 all the way out to 5. So here's 1, 2, 3, 4, 5. And, obviously if I plugged in a 5 squared is going to be 25 and we'll be way up here. And, at 1 squared we'll be down here at 1. So, you can worry about whether you're making this graph to scale or not. So, we know that the shape of a parabola is going to look something like so. Obviously, we also have the point 0, 0. But, as we're looking right here, wow, we've got n is equal to 8. Do we need to draw literally 8 rectangles in such a problem? The wonderful news is no, you don't. What we are going to do, however, is we want to at least draw the first rectangle and the last rectangle. Look, we already said that delta x was b minus a all over n. And if we're going from 1 to 5, well, we know that this is our a and this is our b. So we'd have 5 minus 1. We're already told that we'd have 8 rectangles. So that's going to be 4 all over 8. Which is actually 1/2. So we're going to have rectangles with a base of 1/2. And wow, that can be very, very helpful. It wouldn't be super, super, super difficult for us to go ahead and actually create a picture with the 8 rectangles. But the more rectangles you have, the more cumbersome and tedious it is. So look, for A, we're going to have LRAM. Let's just jump to LRAM real quickly. And LRAM means that the left endpoint is going to do the trick. So look, I'm going to go from 1 to 1.5. That's my delta x. Here's 5, and over here is 4.5. And tell you what, I'm going to start off with a color. Maybe we'll start off with blue. Let's maybe start with blue here. And if I were to look, here's my base from 1 to 1.5. My left endpoint's determined by 1. You might say, how do you know that? Well, look at your interval from 1 to 1.5. That's your left. You can see we're going to go from here. Look, from 4.5 to 5. 5's on the right side, 4.5 is on the left. So we could say, look, the left endpoint determines how tall we really are. Now, for LRAM, if we were to go back real quickly, and if we were to look at this right here, that could get to look rather confusing, seeing that sigma. You see that sigma, and you'd say, well, what did that mean? Well, it meant sum. It meant add. And that's where this formula right here is going to be. We're going to say add. Add up a sequence of base times height. Base times height, or ironically, we could have height times base if you'd like. But what we're really going to wind up doing is, if you think about this, your expression, really what determines your height? Well, your height's always going to be the y value on the curve. It's going to be x squared. And what's your base here? Well, your base is always delta x. And delta x in this problem is going to be 1/2. So we're going to have 1/2 times x squared. And the calculator, when we write this out, some sequence, that's really a way to write out our sigma. So look, just writing this out real quickly, this is how we're going to type it into the calculator. Sum sequence, and we'll get to typing it into the calculator in just a moment. Well, we need to find the area of a rectangle. It's always base times height. 1/2. Well, what's your height? It's x squared, right? Here's your base times height. And then we're going to say, with respect to x, we're always going to put comma x. You'd say, well, what's your starting x value? Well, look at this right here. What's your first left endpoint? Well, it's 1. And what's your ending x value? Well, you can see the last x value that I'm using to determine the height of my rectangle is 4.5. And then finally, you'd say, well, what's your step? Your step will always, always, always be delta x, no exceptions. And that's delta x for your base right here as well. So, as we work through this, let's get the calculator up. And the cool thing is, whether you're using, an older calculator model or not, it's honestly going to be pretty much the same thing. Now, finding sum and sequence, if you look at the 0 button, you've got the catalog button. So I'll go second catalog. And right now, to go to the S is right here by the LN button. So even if you type that real quickly, just hit the LN button, you'll be able to come down and just eventually down arrow till you get to the sum. Now, there are other ways you can do this, but the sum sequence button is really, really, these commands are easily found this way. So we'll go sum. Then what? Well, I'm going to go second catalog again. And, again, I'll hit the LN button. We need to go to sequence, so we'll just bring this down. And the cool thing is, once you've done this, you're not going to have to always go through these buttons. You can use a shortcut later on. So we'll go sum sequence. 1/2 is 0.5. And we'll say times x squared. We'll hit the comma. The comma is right above the 7. We'll say with respect to x, hit the comma again, right above the 7. Say 1, comma, 4.5. comma, and then we could say, well, 1/2, that's 0.5. And the beauty of this is, once you hit enter, what you're really saying is, please add up all of these base times heights. Your x values are going to go from 1 all the way up to 4.5. We'll advance our x's by a step of 1/2. And keep advancing your x's by steps of 1/2 until you get to the end of 4.5. You just hit enter, and my word, you'll get 35.5. And that's your answer for LRAM. We're going to pick up in just a moment and do RRAM. You're going to see it's virtually the same exact thing.